Worksheet 4A, statically indeterminate structure. So there is a ridges bar A, B, C, D, the horizontal gray bar that you see that supported by 2014 T4 aluminum, and so that will be this is aluminum, and also steel rod. So that is steel rod ST, and the support P equal to 120 kips at point D at shown there, and find the axial stress in the two rod. Axial stress in the two rod. So axial stress is mean the normal stress sigma, right? So that will be what is the sigma aluminum, and what is the sigma of the steel on the aluminum and steel rod, and find the deflection at point D. So deflection of point D, that basically with that load applied, what is delta D, the point D going down, how much, that is the deflection at point D. So those are the questions asked, and they give us the information about the length for each rod, also the cross-sectional areas for each rod, the Young modulus, the modulus of elasticity for each rod. By the way, if they don't give us, we can be able to go to appendix B to find that down, and they give us the yielding stress for aluminum rods is 41 ksi, and for steel, A36 steel, at that name implied, the yielding stress is 36 ksi. So from that, we can do this problem. Start with, just like engineering mechanics, start with free body diagram. So let's draw the free body diagram for each, and let's draw together for all of the members here. Here we have 3 members, A, B, C, D. Consider ridges as the problem give you, and then the deformable body, aluminum rod hooked to ABCD at B, and the steel rod hooked to ABCD, the horizontal bar at C. So that is 3 members. So in here we draw together your 3 members, separate each of them, but draw in holistically here so we can see the big picture. So the first one, I draw the horizontal bar ABCD. So that one here, we have A, then 12, 12, and 6. So it's 12, 12, and 6. So we have A, we have point B, we have point C, and we have point D there. So let me, so as you see the demonstration about the compatibility diagram in the lecture, if we apply the load 120 kips at point D going down, as you can see here, then the most likely, because it reaches ABCD reaches, so it will be going down, but still keep the same straight member. So from that, as you can see here, for aluminum body, B now go to B apostrophe, and then B now go to B apostrophe. Let me change it here, change the color so that go down here, it B apostrophe. So then C go to C apostrophe, and D go to D apostrophe here. So from that, as you can see, in terms of the length, aluminum rods increase in the length from B to B, but now it go down to B apostrophe, as you can see there. So the length increasing, which is the aluminum rod, it in tension because it extend the length. Now go back to the steel rod, as you can see C, go to C apostrophe, the length, effective length of the steel rod it going down, it reduced. So with that, as you can see, the steel rod will be in compression. So with that, we can draw the free body diagram for the aluminum rod and the steel rod. So for the aluminum rod and for steel rod. So as you can see, free body diagram, basically we isolate each body throughout its surrounding. So from there, you can see the aluminum rod is tension. So it will be, when you isolate, it go up your cut. The load will be go up your cut. And to be equilibrium at point B here, then the load, the force that aluminum rod apply on ABCD will be going up to be in equilibrium. See that there? It go down on the aluminum rod to maintain that aluminum rod is in tension, so that it will be extend the length, and then the reaction from the aluminum rod on ABCD have to go up to cancel out. See that one there. Similarly, at C, since the rod steel rod have to be in compression, so the force applied on that rod have to be go into the section. What does that mean? And you can see invisibly that at that load here, that basically the load of member ABCD, the horizontal member, apply on the steel rod, and at the same time, your Newton's third law, the reaction from the steel rod, all the member have to be equal and in opposite direction, equal in opposite. So it will be going up, and so it's the same magnitude. So let's call that reaction. As you can see at B here is By. Similar, we have C is Cy, and then every reaction here, Cy, go up, go down, for depends on the member we are talking about. For example, ABCD, Cy going up on ABCD and going down at the joint C on the steel rod. Similar for By. And now we remove the pin A's out of the rigid body ABCD, rigid bar ABCD, that the problem gives us the pins. So you have two unknowns here. You have AY and you have AX, and that nothing news to us. That's nothing new. And then we can assume X and Y. So basically here we draw free body diagram, right? One for the horizontal bar ABCD, one for the steel rod, and one for aluminum rod. And we use the Newton third law to make sure we draw program correctly. And for this one, don't just randomly assume the direction of the steel aluminum rods. We need to be consistent in terms of the behavior of the steel or aluminum rods, whether they are in tension or in compression. Depends on, and you can see when you observe, if it increase the length, then it in tension. If it reduce the length, contraction, then it in compression. And this is a very good example to show both scenarios. Aluminum rod, the top one, in tension, the deformation will be positive. The length of the rod will be increasing. If we apply 120 kips that going down at D, the steel rod, the bottom one, it will be in compression because the length, it will be contract, and that due to the load 120 kips apply down at point D. So that's the free body diagram, and then we can go ahead to fill all of the information of the length. So that is 12 inches, and 6 inches. Okay, so from that we can go ahead to write the equation. So let's write equation of equilibrium equation of equilibrium. Equation of equilibrium. So let's make it fast in here. Sum of all the force in x direction equal to 0, and in this case only ax. Let's call that equation 1. And then we have sum of all the force in y direction, assume going up equals 0. So you have that equal to a y on member ABCD. So we have it plus by also going up on ABCD, and also cy also going up on member ABCD at the free body diagram shown. And we have 120 gives at point D that we missing in there. So it will be negative going down. So it will be negative 120 equal to 0. That we have equation 2. And the next equation, it will be moment. Sum of all the moment. Moment about which point? You can select any point. Let's make life easy. Take moment about A equals 0. So you will have, and assume counterclockwise. So you will have by time moment arm 12 plus cy also counterclockwise on member ABCD about A. So cy times 24. And then 120 about A on member ABCD, it clockwise, so negative 120. 120 times 12, 24, 6, so it will be 30. And that equation is number 3. And how many unknowns in here? You have AX, AY, BY, and CY. So basically 4 unknowns, 3 equations. So 3 equations and 4 unknowns. 4 unknowns. So basically we cannot solve it, and it's a happy pace that what you learn in you learn in energy mechanics, and that structure that you don't have enough equilibrium equation to solve for the unknown reaction. That structure we call it here statically indeterminate structure. So energy mechanics static alone cannot solve that problem. So with that, so don't just only use the static, you have to use the information in this class to solve this. So that here we can say that here statically indeterminate. So from the lesson note, if you recall, for the statically indeterminate, we need to use the compatibility diagram to solve the deformation. So let me draw the compatibility diagram in here for this case. So let's draw the compatibility diagram. And if you recall that we call it CD. So from this you can use the Richards bar to draw. So you have Richards bar here, and we just see how it deflects. So now when it going down with the load 100, and I exaggerate that deflection to make it bigger so that we can easy to visualize. Yeah. So from that we have point A, we have point B, and we have point C, and we have point D, and it will be going down here, B apostrophe, C apostrophe, and D apostrophe. And that distance, that's distance here, we call it delta B. Distance here, we call it delta C. And the distance here, if you want, it will be for that deflection, delta D. Delta D. This is delta B. Delta B. And delta B, delta D, basically that is the delta, the deformation of the aluminum and steel. So basically that equal to delta of the aluminum, deformation of the aluminum rod. And C, as you can see here, the C, go to C apostrophe, the steel rod tend to be contracted, and that basically delta C here is the axial deformation of the steel. So from that we can write equation with the compatibility diagram in here. So what is the equation? So you have the two rod, aluminum and steel, and we have the distance here is same 12 inches, 6 inches. So we have the equation from the compatibility diagram that can be written as delta B over 12 inches equal to delta C over 24 inches. If you are not sure what is that about, we use the similar triangles AB, B apostrophe, AC, C apostrophe to get that ratio. And that another equation to solve, right? So let's elaborate that equation out. And I already say delta B equal to aluminum deformation of the aluminum rod. So from that we can have delta B equal to the deformation of aluminum rod. And for the actual deformation, if you recall from our class, the deformation equal to P from the actual deformation note, as you can see here. And we also need to check assumption later on to have that equation. PL over AE, right? PL over AE. Let's go back to here. PL over AE. So that it equal to PL. So the load on the rod, right, over AE for aluminum rod. And then we also have delta C equal to the deformation in steel rod, and it equal to the equation PL over AE. And be mindful, what is P? That is the actual load applied on that member. So what is that about? What is the actual load applied on that member? Let's elaborate out here in that side. Elaborate out. So as you can see here, load applied on that member. For example, the P in aluminum actually be white. Because that here also be white. That here also CY. So the load applied on the member is B. For aluminum rod is BY. For steel rod is CY. So it's not 120 kips when you plug the P in there. And go back to here to the equation here. The P here is applied on the member that we want to find out the actual deformation. Make sense? So with that, go back to here. We can plug with that equation 4. Let's call that equation 4 become equation 4 become when we plug delta B equal to that in. So we can have the same equation here. So with delta B, so you have that is, like I say, P is BY. So we have it BY for the aluminum, that is the load P on steel rod, time L of steel rod is 10 inch, And for aluminum rod, also 10 inches. So that we can put the L naught here is times 10 inches over 12 inches in that equation. Okay, 12 inches. Let's write down 12 inches. 12 inches in that equation first. And then we have AE as well. AE for aluminum. So we will have A, which is the area. What is the area for the aluminum rods? 10 inches square. Area for steel, 2 inches square. So plug in for the aluminum. It will be 8 inches square. Times the E, modulus of elasticity for aluminum rods is 10,600 ksi, which is perfect for the unit here because square inch and ksi, and the problem give us 120 kip, so that is perfect for the unit, so without the conversion here. So 10,600 ksi. So that is from the left side of the equation, delta B over 12 inches. And now write the right side of that equation, delta C over 24. Delta C equal to PLAE for steel. So it will be CY, as I mentioned earlier. So it will be CY times the length of that rod is still 10 inches. So 10 inches. Divide by 24 from that 24 inches. Times the area times E. So area in this case, I think it's 2 inches square. So 2 inches square. Times the Young modulus for steel, 29,600. 29,600. 29,600 KSI keeps per square inch. From that, I can simplify equation 4. Equation 4 is very simple. By minus 0.731. Your job have to simplify this. 10 inches, for example, 10 inches, cancel, etc. CY, check that one. And you have to practice this. Equal to 0. And that's equation 4 now become this. So from the compatibility diagram in here, delta B over 12 inches equal to delta C 24 inches. Apply the axial deformation, right? So let's write down here. It's basically axial deformation. Write down big here, axial deformation. We have that equation. Okay, still not good here. Write down 5 here, axial deformation. Perfect. So we have that equation 4. So when you have equation 4, and now we have 4 equation, 4 nodes, right? So now we already have 4 equation and 4 unknowns, and that will be a happy phase. What are the 4 equations? The 3 equation in equation of equilibrium equation and 1 equation from compatibility diagram. So it will be happy phase, and that you can go ahead to solve. So because the first equation 1, we already know AX equals 0. So just equation 2, 3, and 4, right? To solve AY, BY, and CY. So let's use, we can use equation 2, equation 3, and equation 4. So with that, we use equation 2, 3, and 4. So set up that equation in calculator. So with the matrix, as you can see there, for the first one I can have ax, ay, by plus cy for equation 2. Negative 120, I click on the other side for negative 120 become 120, right? So you have 1 for the coefficient, and we have it in that order: ay, by, and cy. It equal to 120 for the equation number 2. And then we have equation 3, by 12, cy 24, and negative 120 times 30. 120 times 30 is 3600. Put in the other side, it become positive. So 3600, and no ay, so it will be 0, 12, and 24 for cy. And then that equation 3. Now equation 4, by negative 0.731. So you have that is 0, 1 for b, and negative 0.731 for cy. And the equation on the right side equal to 0. So from that, use your calculator, substitute whatever that you learn, and then you can find out ay equal to negative 70.15 gives by equal to 30.3 gives, and then you have cy equal to 109 times 85 gives. Are we done yet? No, not yet. The question asks is, what is the actual stress in the two rod and the deflection at point D? So you have to find out that, right? So axial stress, it means the normal stress in here. So we have to find out the axial stress. Axial stress. So with the axial stress, we have sigma for the aluminum rod. It equal to, if you recall, it P over A, right? P over A. Let's put it P over A for the aluminum, if you recall that. So the load on that member divided by the area of that member. So in this case, it basically that on the member, the load P here on the aluminum rod is by. So it will be equal to by over A aluminum, and that we already have by is 80.3 divided by aluminum area 8 inches square. Problem give you 8 inches, so that you get 10.04 gibbs over square inches. So it will be KSI, and that is in tension. And we reasoned before, because the aluminum rod is extending the length, and steel rod, it will be in compression because it's trying to contract the length of that rod. And then we have the sigma steel rod also equal to P over A. Don't just put the 120 here, right? Equal to the load on that member. So it cy, so basically cy over areas of the steel, and plug in cy in that case, and you can see 109.85 divided by 2 square inch for steel rod here, 2 square inch. So from that we will have equal to 59.9 KSI and compression. Are we done for this problem? Are we okay after we find out the axial stress on aluminum and steel rod is done? The answer is not yet. That's not easy. Go back to our note here. When we have this deformation, delta equal to PL over AE, several assumptions need to be made. First, it have to be homogeneous. That's good because that is still isotropic. So we have sigma over PA, good. Because that's steel and aluminum. It holds those two. Cross section, constant. Cross section, yes. Aluminum 2 inches square. No, aluminum is 8 inches square and steel is 2 inches square. So the first three assumptions is correct. Now it's elastic. To have that E equals sigma over epsilon, so that we can transfer the delta equal to epsilon L naught and epsilon equal to sigma over E. That have to be elastic. And go back to elastic. And we assume the behavior is elastoplastic behavior, which is that the maximum stress that they can have is the yielding stress. We ignore the ultimate stress in here for the conservative assumption. So it's poorly elastic linear portion at the beginning and then horizontal, so maintain the yielding stress for the whole behavior until it rupture. So with that, as you can see, with that modeling performance, elastoplastic, the axial stress have to be less than the yielding stress to be in elastic region, so that we can have delta equal to PL over AE that we use for the problem. So as you can see, it have to be inelastic to make this problem correct. Otherwise, plastic, then the sigma maximum it can get in here, as you can see the yielding stress because it's horizontal line over there. So with that, we have to check our assumption, and that's very important here. Don't ignore this. Okay, check assumption. Excuse me. Check assumption. What assumption need to be checked? I just mentioned earlier, it needs to be elastic. So, elastic, in elastic region, to be able to use the equation which is delta equal to P L over AE. So from that, because we use that, it have to elastic. And in the elastic region, with the elastoplastic behavior, when we model the performance of the material, then the actual, sigma actual on the body have to be less than the yielding stress of that material. So from that we can have, let's check. For the aluminum, we have sigma aluminum for the actual equal to here 10.04 KSI. What is the yielding stress for aluminum? 41 KSI, and for steel 36 KSI. So as you can see, it have to be compared to sigma yielding for aluminum, that is 41 KSI, and it actually less than, so it's okay. That one is okay, good. So our elastic assumption is good. Now go to the sigma for steel. It equal to, we have 59.9 KSI, and it have to be less than or not for the sigma yield for steel, and that is, I showed you earlier for the problem, steel is 36 KSI in here, 36 for steel. So plug in here, it's 36 KSI. Whether it's 59.9 less than 36? No, so that is not okay. So it means our assumption that the body, the rod in elastic region is not correct. So that you can see what does that mean here. If not, then we have the steel rod is plastic. So when a steel rod is plastic, then what you can say? Then we only have, when that we have sigma steel on that member, the actual stress on that member have to be equal to the yielding stress of the steel equal to 36 ksi. Because as you can see from the elastoplastic behavior, the maximum for a material is sigma steel, the horizontal go to there. So from that we can have, now we have that already, so we can see the sigma steel equal to, for the steel rod equal to yielding stress for that one 36. So from that we can have, because that's sigma, so when you have the actual normal stress 36, then you can go ahead to find out the P, the load on the steel rod, and that basically a Cy. So that Cy equal to, because that homogeneous and isotropics, we always have the equation sigma over P equal to P over A. So from that we have P equal to sigma A. In that case, we have the P index here for steel rod is Cy, and it equal to sigma A. So it will be equal to sigma of the steel rod actual apply on steel rod time the area of steel rod, and that equal to 36 ksi time 2 inches square, and that it will be 72 ksi keeps per square inch square time inch square, so cancel the inch square, so you will have kips. Okay, and that is Cy. And then we have By. Here it equal to, and if you want it, the direction is it will be, as you can see, positive here, so go up on member ABCD, go up on ABCD, and compression for that member. So By, how can we find out By? That is from equation 3. We cannot use equation 4 anymore, because equation 4, based on our assumption, is using axial deformation, and that have to be in elastic region. One of the member, which is steel rod, is in plastic, so the equation 4 now become invalid. But we have another equation is, we are in plastic, so we have the equation is sigma steel equal to the yielding stress 36. So that use that equation instead of equation 4. So that basically the new equation here, actually that equation 5 there, right? So use 5 instead of 4, right? Replace 4, that replace, so they can use both, replace equation 4. Make sense? So from that we plug to the equilibrium equation, because that always valid regardless of how the behavior is, and that equation from equation 3 we already know Cy, so you can find out By. So it will be from equation 3 we have By equal to 3600 minus Cy, Cy times 24, and Cy equal to 72 kip. 72 kips, and divide by 12. So from that we will have equal to 156 kips. So from that we can By, that is the load on the aluminum, so we can now recalculate the sigma for aluminum. Sigma for aluminum, normal stress on aluminum, is equal to the load by on that aluminum. So 156 divided by the areas, 8 inches square, right? Keeps 5 by 8 inches square. So from that we have 19.5 KSI, and that we have to check with the sigma yielding stress for the aluminum, and that 41 KSI still good. So it's okay. It's okay. So from that, what do I mean? Here we have the answer for the aluminum axial load, axial stress on aluminum is 19.5 KSI. And for the steel, because in plastic, the maximum they can get is 36. So that it will be the answer for steel. And the last one is the question is deflection at D. The last equation they want is the what is the deflection at D. So let's do that. Deflection at D, and that will be a delta D. And that delta D, we can use the similar triangles in the compatibility diagram, AB, B apostrophe, and AD, D apostrophe, AB, B apostrophe, and AD. So with that similar triangle, I can have in the compatibility diagram, we can have that delta B over 12 inches equal to delta D over 30 inches. So you see this is a long solution, right? But that's what we need to do. And that is delta D equal to 30 divided by 12 delta B, so that it will be delta of the aluminum. And why we can use that? Because that aluminum still in plastic, because it's in elastic region, because it's less than the 19.5 KSI, less than the aluminum normal stress with yield stress, which is 41 KSI. So we can plug in 30 divided by 12 delta deformation equal to P over LA. So that is PL over AE for aluminum, and that P equals to BY, so it will be 30 divided by 12 BY 156 L 10 inches divided by areas 8 inches square, Young modulus 10,600 KSI. So from that we can have delta D equal to 0.046 inch, and that going down, and you can see it deflection down, so that should be the answer. Now the final thing we want to emphasize on this problem, can we use the similar triangles in the compatibility diagram that appear here, which is similar triangle? Instead of I use AB, B apostrophe, and ADD apostrophe, can I use AC, C apostrophe, and ADD apostrophe? The answer is yes, you can use that, but the problem here is when we find out the delta C, the delta C is not the deformation of the steel anymore, that you can apply PL over AE, because that equation for steel is no longer valid, because the steel rod in this case is in plastic. So let me make a note here. Yeah, cannot solve using delta C for delta B, right? Since steel rod is plastic. Keep that in mind. Wow, we finished this problem. My forehead it get wet because of a very long solution here, but I want to make it in one video so you see the whole picture of this problem. Good luck with everyone. You see very important problem. Let's take a look on of this and practice the next problem by your own, which is worksheet 4B.